Okay, so today we're going to talk about the periodic table generally. So I'm going to keep going back and forth to my periodic table here. I have a couple other visual aids, but we're going to sort of familiarize ourselves with the periodic table. So the way the periodic table came about was because early in the 19th century, so early 1800s, scientists were really kind of raring and going about collecting, finding elements, categorizing them, finding about their physical and chemical properties, and really collecting a huge amount of information, and it was taking up books and books and books. And they needed a way to organize it. And this guy came along, Dmitri Mendeleev, and he discovered what we now call periodic law and organized it into what's called the periodic table. So periodic law is, well, I think it'd be easiest just to show you. When what Mendeleev did was he took the elements and he took them in order of their mass, because he didn't actually know about protons and neutrons and atomic number and all that. The modern day periodic table is based on atomic number, but at the time he didn't have anything to go on. So he just listed them in order. Fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. And I don't think I missed any, but I did forget my G there for some reason. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen. Well, that's not very good. Nitrogen, oxygen. Okay, so there they all are. And what he did was he just looked at their properties, and he noticed some funny things happen. He noticed that hydrogen, lithium, sodium, I'm going to add one or two extras to make the point, potassium, calcium, and he noticed that potassium all had really similar properties. He then noticed that beryllium, magnesium, calcium all had really similar properties. He then noticed that boron and aluminum had really similar properties. And carbon, silicon, nitrogen, and phosphorus oh, I didn't get oxygen written down when I did it again. Oxygen and sulfur, and so on and so forth. So you notice there's this, he kept seeing this repetition. This one, this one, this one, this one, this one. And actually it turns out that, so helium's kind of here being left by itself. Helium, neon, argon, and then I guess the last one I need to deal with is chlorine and fluorine. So what he's noticing, except for this first bit here, he would actually notice that there was a repeating pattern. And so notice I got red circle, black circle, red square, blue square, black square, blue triangle, black triangle. Same order here, and same order here. He started noticing that there was this repeating pattern to sort of the chemical properties, that we would get something like sodium, and then something like magnesium, and then something like aluminum, and then something blah, blah, blah. So what he did was he organized it in such a way to put the elements with similar properties in the same column. So if you look, hydrogen, lithium, sodium, potassium are all in the same column. Beryllium, magnesium, calcium all in the same. Boron, aluminum. Are all in the same column. So this became known as a periodic table. So this thing here, and we have groups and periods. So groups are the vertical columns. Periods are these. These are periods. So the rows. Now, let's go back here. Oh, there's a better one. So groups, periods. Oh, and so these two things here at the bottom, these two rows down at the bottom, they actually belong here. This is what the periodic table would actually look like if we didn't chunk these bits out. It just makes it kind of long, and we don't use these elements too much anyway. So we're going to mostly ignore them, and they kind of just get to live down here. But realize that, notice it goes element 57, 58 through 71, and then 72. So there's a break here. So, you know, we can just keep them down there for a while. So he found that each column has elements of different properties. So the columns are named in two different ways. We go back here. Notice there's two different sets of names, and the periodic table in the classroom has both of these on it. There's the older way with these 1A, 2A, bizarrely 3B, 4B, 5B, 6, 7, 8B, and then 1, 2, and then 3A, 4A, 5A, 6A, 7A, 8A, and then the newer naming 1 through 18. Now, this may sound hard to believe, but the newer naming, the 1 to 18, is kind of useless and silly, because 1 through 18, these numbers don't mean anything. This may seem really strange, but these, all these group 1A, 2A, all this stuff, they actually mean something. And so I'm going to often refer to them by this older naming convention, just because the newer naming convention, though simpler, has no meaning and is therefore kind of useless in itself. So, so there it is. So that's how they're named. Some columns do have special names. I do expect you to know these column names. So I'm going to go back to this periodic table here. So group 1A are called alkali metals. So here are the groups. So alkali metals, alkaline earth metals, halogens, noble gases. Group 1A are the alkali metals. Group 2A are the alkaline earth metals. Group 7A are the halogens, and group 8A are the noble gases. Okay, we can break the things on the periodic table out into some other categories, like main group elements, which are just the A groups. So if we look at the periodic table here, the A groups are the main group elements. So these ones that stick up above everyone else. And they're kind of cool in that they have nice predictable patterns, nice predictable reactivities. Their reactivities, they more than anyone else, any other groups, they fit in that pattern of in the same column they have the same properties, and their properties change in a nice predictable way from going across the periodic table. So as you move up, down, left, right in the main group elements, their properties change in a real predictable way. The transition elements are that lower bit. They're the B groups, and they're a little bit less predictable. And they're a little bit less predictable. Their properties are a lot more similar, and therefore they're kind of harder to distinguish. And so these are the transition elements. We're not going to talk about them as much as the main group. We'll talk about the main groups a lot, and the transitions a little less. And finally, the inner transition elements are these two at the bottom. We're not going to hardly talk about them at all. We're just going to ignore them for now. This kind of ends up being more of the realm of physicists because they have more interesting nuclear properties, and their chemical properties are not. Some of them had some interesting chemical properties, but by and large, they don't. They're not chemically very distinguishable. They're not very interesting, though they can be. Okay. Furthermore, we can classify all elements on the periodic table as metals, and so metals are really, they're mostly classified by elements that, an element which is shiny, conducts electricity, is ductile, means it can be pulled into wires, malleable, can be formed into sheets, and forms alloys, which are homogeneous mixtures of metals, because they can you can melt them and mix them together. They tend to lose electrons in chemical reactions. I got to say that this is probably the most noteworthy thing about metals, that they tend to lose electrons. So that's, that's probably the most noteworthy thing about them. Nonmetals simply lack those properties, but most noteworthy, they tend to gain electrons in chemical reactions. So metals tend to lose them, nonmetals tend to gain them. So I'm talking about gaining and losing electrons in chemical reactions, right? So remember, electrons are farthest on the outside, right? So that they are the things that can be gained or lost. That's why nuclear changes are not very common. because it's harder for the atom to gain or lose things out of its nucleus because it's buried on the inside. Electrons are easy. Electrons are all on the outside in that cloud, and they can lose them easily. So here's sort of a breakdown of metals versus nonmetals. Metalloids are elements that have some properties of one and some of the other. And here's how you can identify by looking at the periodic table which elements are metals and which are metalloids and which are nonmetals. If you look here, there's this big, heavy, stair-steppy line. This line divides the metals from the nonmetals. So, over on the left-hand side over here, these are all the metals. This includes the inner transition elements. Nonmetals are over here. So you can see there's a lot more metals than there are nonmetals. So metals are much more common in the universe than nonmetals. Now, so metals, so these are the things that tend to lose electrons, and they tend to have, what am I trying to say? They lose electrons, and they tend to have those properties of like conductive and ductile and all that sort of thing, shiny, that sort of thing. Here's the nonmetals, they tend to gain electrons. Now, right on the stair-step line, not diagonally touching, but if it has to share a border with the stair-step line, these are all metalloids, right? These are all metalloids. Now, I don't know why this is A and E. This is actually gallium and germanium. But these are all metalloids. And I don't know why that's A. Let me go to a different periodic table.